Hi, in this video, I'm going to explain the basic idea of the sliding mode control. Often, the dynamic of the system cannot be changed by the designer to improve the system performance, and that's why we need a controller to generate a control law, enable the system to achieve the desired performance. In this video, we're going to focus on the sliding mode control and how we can make the sliding mode control for the system to achieve the desired performance. Now, in order to design any controller, we need to have the mathematical model of that system. And in this video, we will assume that you have a background about state space modeling of the system. Sometimes there's a difference between the mathematical model of the system and the actual system. So when you try to model the system, you are not develop accurate mathematical model of the reality, the real system. Now, this mismatch could be because there is unmodeled dynamic of the system, or like there's a variation in the system parameter, or the approximation of complex behavior of the system is not accurate enough. Now, because of this uncertainty, the controller will not be able to produce the required performance. And that's why we need a robust control. And here we have the sliding mode control. It's considered one of the robust control, and also the power of a sliding mode control is to deal with the nonlinear system. Now, before we go to the basic idea of the sliding mode control, let's understand what the idea of the phase plane analysis. Now, the phase plane analysis is like a graphical method to study the second order system with respect to the initial condition. Now, that's why we assume in this video our system is second order system. So the video or this lecture is focused or limited to the second order and nonlinear system has uncertainty. Now, the idea of the phase plane is to provide the motion trajectory corresponding to various initial conditions. So if you have a system and I give him initial condition, the phase plane will give you like how your system will move until it gets to the original stability. And we could examine the feature of that trajectory, and also we could obtain some information about the stability. Now let's have this example. Imagine you have like a pendulum system, and x is the state, the first state of the system, which is the theta, and x dot is the angular velocity omega. Now if we have this pendulum and we just move this pendulum for certain theta, which is this one, and we remove we leave the pendulum. Now, what will happen? The pendulum will move until it gets to theta equal to 0. And that's what explained here in the phase plane. So the system will have energy, which is moved until he gets there. And when it gets there, this is the theta equal to 0. Now, you start from this theta, but because there is damping, like the air or some energy is losing. So when the pendulum is get there, the theta is not the same as this one, like less, and in the negative, because this is the positive, this is the negative. Now, because we're moving in this direction, our velocity, because this is the velocity, this is the positive part, and this is the negative part, we are the negative part. Now, when we move in this direction, the same direction of when we move, so it's become the positive, but I'm still in the negative as the theta. Now, I will get to 0 again, which is this one, the 0, but in the positive. And then I will go back again to the same direction, but I start from this theta. Now I am in this theta, and the second cycle in this theta until I get to the equilibrium. So this is the idea what the phase plane is doing, is just provide you the trajectory, how your system behave, how the energy of your system is behaving until your system get to the equilibrium point, get to 0. We assume there is like a damping in that system, so the pendulum will move until it settles down in the 0. So if you understand this point of the phase plane, let's go to explain what the meaning of sliding mode control. In the sliding mode control, the control U, to design the control U, we will split the control U into two regions. The first one is the sliding surface. So what's the meaning of the sliding surface? Imagine you have like this surface from like two variables, x and y. And you have this equation, 2y plus 5x equal to 10. So if you want to plot this line, all you do is just set x equal to 0 and y is like 10 over 2, so it's 5. And then we put y is 0, so x is 10 over 5, so it's 2. So this is the line to represent this equation. Now, as we could say, this surface, what is doing here, the first region is the surface. So we could say this is like surface S, which is equal to 10. So the surface contains two variables, and the value of that surface is 10. We could have like surface equal to 10, and if we move in this direction, we go to the S equal to 0, and if we move in this direction, we go to the S equal to minus 10. So this is the line. And this is the surface we needed for our discussion in the sliding mode. Now, if you have an initial condition, all you want to know is you need to find a surface to slide on. Now, the best surface you could slide on is with S equal to 0. Because if you are reaching to this slide and you're just sliding on this surface, you will get to the equilibrium point, which is 0. So now, the question is how we could make this point, which is like the initial condition of a system or the condition of the system, how we could move it to this surface, which is equal to 0. So we could ensure that if this point go to the S, will be sliding up to the 0. Now, so the first thing is we find the S equal to 0. The second is how we could make this, so how the control law U make this initial condition enforce the system to slide on this surface. Now, if we assume this is the slide on the positive and this is on the negative. So when you are in the positive, you don't need to go up there. You need to go in this direction. So if you are in this initial position, you need the next position is this. And then until you get to this slide. Now, in order to make this clear, now, if you are at this point, so the derivative of your motion should be in the negative. So if you are in the positive side, and like imagine you are in the S equal to 10, so you need to move to S equal to 5, and then 4, and 3, until you get to the 0. So your motion should be in the negative. The derivative of your motion should be in the negative. So if you are in the positive side, your derivative should be in the negative. Now, if you are in the negative side, like minus 10, you need to be like minus 8, minus 6 until you get to the 0. So if you are in the negative side, you don't need to go to this direction. So if you are in the negative side, your derivative should be in the positive. Now, in order to put this in a mathematical formula, what we can say, the derivative of your motion should be minus of the sine of your surface, which is the surface S. Now, if your surface in the positive, so the sign is positive, multiply by negative, so the derivative should be in the negative. And if your surface in the negative, the sign is minus, multiply by minus, so the derivative is positive. And this is what we call it the reaching mode. So the control law should first ensure that the system moving to the S equal to the 0, and also the S dot, which is the derivative of the slide, equal to this, which is the reaching mode. Now, if we go back to our equation, now all we need, if we substitute this 10 by S, so we need to find, like imagine you have system with two order, like x and x dot, and x equal to x1, and x dot is x2. So all you need is to find this equation, which is ax1 plus x2. This surface will make S equal to 0. So this is the sliding surface, and this is the reaching mode. This is the two part of the control law and the control action. So the key in the sliding mode is to find this the best sliding surface, which is ensure that S equal to the 0. And if the initial condition of the system go to this surface, will go to 0. Now, if we want to set this in a formal way, so imagine you start from the initial condition S. So all you need is to find the reaching mode that ensure this initial condition will go to this sliding surface, and you have to ensure that this sliding surface is equal to the 0. So the system will slide until it goes to the 0. Now, there's a problem, which is the chattering problem. Because this is like a switching, so if you go on this side, you have to go back. So like your controller should be switching. So there are many paper discuss the idea of chattering, and they find like different reaching mode, and we will just discuss this in the video. In the literature of the sliding mode control, many reaching mode or reaching low have been proposed. So, for example, it could be used the first, the basic one, which is they name it constant rate, which is just minus k multiplied by the sign of the sliding surface, where k is larger than 0. The other one is constant with the proportional rate. So the first part is the constant and with other k, which is the proportional. And there's also the power rate, which is minus k absolute up to the gamma sine the surface. So there's also there are many other reaching low have been proposed in the literature of the sliding mode control. For this video, I will use the power rate type, or the power rate reaching low, which is minus k absolute the sliding surface up to the gamma, whereas k should be larger than 0 and gamma between 0 and 1. So we will start with this as a reaching low when we design our control. In control system, we have two problems. The regulator problem, which is a problem should guarantee that your system is stable in the closed loop after we added the controller. So imagine you have started from initial condition of you have any disturbance system. So your system should go to the original, to the equilibrium point, and you could shape this transient response by the regulator. So the problem of regulator is return to the original and how you shape this response up to the original. And there is also the tracking problem when you have a reference and you want to follow this reference with 0 steady state. Now, in the beginning, we will design the controller for regulator. So if you have a regulator, so you start from initial condition, and then you want this initial condition with the reaching mode goes to this sliding surface, and this sliding surface return the system to the origin. So this is the objective, and we are stuck with the system with second order, so the x and x dot. So imagine you have this dynamic system, which is nonlinear system. That's why we put f, which is a function of x and x dots, and this is the control law, and it's varying with time, and also how you have some uncertainty. There is a parameter in your system which has uncertainty, but all we know is the upper bound of these parameters. Now first we have to develop the state space model of the system. So we have x, which is x1, and x dot, which is x2. Now x2 dot will represent the dynamic of the system. The next step is to design the sliding surface, which is S, A x1 plus x2, where A larger than 0. Now, if we take the first derivative of the sliding surface, which is S dot, A x1 dot plus x2 dot. x1 dot is the same as x2, and x2 dot is the dynamic of the system. And we said that we will start with the reaching mode, which is minus k s absolute s up to the gamma sine s. So if we equal this part with this part, we will get this. So this is the s dot, and this is the reaching low. Now if we rearrange this equation by taking u as a parameter we want, and the remaining is in the other side, we will have like u equal to the minus a x2 minus the dynamic of the system, the remaining of the dynamic of the system, minus the reaching low, which is minus k absolute sliding surface up to the gamma sine sliding surface. Now let's take an example and see how we could go with this. Imagine you have this design sliding mode for a system which is x double dot c1 x dot square plus c2x plus u. Now we have a nonlinear system because you have x dot square. So this is the nonlinear system. And also you have the two parameters c1 and c2 as uncertainty. They are uncertain. But they are bounded by c1 and c2. So we know the upper bound of c1 and c2, which is the capital C1 and c2. Now we will design a regulator controller using the sliding mode control. Now this is the dynamic of the system. So we develop the state space, which is x1, x dot is x2, and x2 dot is the dynamic of the system. Now when we model the system, we should keep c1 and c2 as small, which is the parameter has uncertainty. So we don't know how exactly what the value of c1 and c2. Now the sliding surface is a x1 plus x2. The first derivative is a x1 dot and x2 dot. And if we put the dynamic of the system, so this is the s dot a x2 plus c1 x1 x2 square c2 x1 plus u. And this is should be equal to the reaching law. We already said that we will use always this is the reaching law. Now if we equal two parts and we take u, so the remaining is in the other side minus ax2. Now because we don't know c1 and c2 for designing the control law, so we will use the upper bounds capital C1 and capital C2 in our controller. So this is the capital C1 and this is the capital C2 and this is the reaching law. So this is how we will design the control law to regulate our system even with the nonlinearity and have uncertainty. Now let's jump to the Matlab to see how we could go with this. In the Matlab, I already typed the code, so I will just explain the code. We have to have two files, two on file, and they should be in the same folder because we will use the function. Now, in the first file, I will just explain it easily. Is the call function? I just call ODE is used for nonlinear system to simulate nonlinear system. So this is the simulation type. This is the initial condition. I will assume there's initial condition. So I need this system goes to the original, and I just plot the first state with time and also the second state with time. So this is the call function. Now let's go to the function. In the function, I have C1 and C2, but I don't know exactly what is the value of C1 and C2. So thus, I will change the value of C1 and C2 which with each run. But I know the capital C1 and C2. So I know the maximum of small c1 is 5 and the maximum of c2 is like 8. So imagine you have a mass system with the mass, but you don't know how much the mass. But you know that this mass is no longer than like 8 kilo or 5 kilo, something like this. Now A is the parameter of our controller. So this is A. And this is a tuning parameter. So you could choose any value you want, just tune it. K is the other tuning parameter, which is the K. And gamma is PP. I put it like PP in the simulation. This is the gamma. It's between 0 and 1, and I just choose 0.66. Now in the beginning, you have the x dot, which is 0, initial, the derivative of your state. Now this is the sliding surface A multiplied by x1 plus x2. And this is the control law, which is we design it, minus ax2. So you can see minus ax2 minus capital C1, capital C2, multiply the C1 by x2 squared. This is the x1. And this is the reaching law, minus k absolute s up to the pp, which is gamma, multiplied by sine x. So this is how we develop the control law. Now this is the dynamic of the system. You could take it from here. X1 dot is the same x2. So x1 dot is x2. And x2 dot is the dynamic of the system with small c1, c2. Small c1, c2. Now if we run the system, we can see that the system starts from initial condition and goes to the 0. So that's the objective, the regulator. Now imagine your C1 and C2 is not like 0.5. Let's say it's 4. And it's like 7. So that's the uncertainty. We don't know exactly how much C1 and C2. So it's varying. But it's not more than 5 for C1 and not more 8 for C2. Now if we save the file and run the call, you will see the response is different. But again, the system goes to the 0. So whenever the value is less than 8, so let's go to, like, for example, 2 and 5. You can choose any value which is less than the upper bounded, and you simulate the system, and you will see the shape of the response may be changed, but the system goes to 0. So this is how the sliding mode control is implemented for regulator. Now we will go to see how the sliding mode control could be designed with the referring, with the tracking for a certain reference.
Now let's see how we could design the control law for the tracking problem based on the sliding mode control. Now instead of having x1 and x2, in the tracking problem you have E and E dot. Because you have tracking, so you have a desired value and you have the actual value, and your actual value should follow the desired. So you will start from initial error, and all we need is we find the reaching mode to take this initial to this sliding surface until we get to the desired final value, which is the 0. The dynamic of the system is the same as the regulator. Nonlinear system has uncertainty bounded by the upper value, and the same with the state space modeling. The sliding surface now is different by assuming that the sliding surface is AE plus E dot. Now E is the reference minus the state, and the E dot is the reference dot minus the state, the dot, or the derivative of the state. Now if we substitute this, we will get this. This is the error plus this is the error dot. Now we will substitute the x by x1 and the x dot by x2. Now in this video we will consider that the xr is constant, and this is limited for this video. Now if your reference is differentiated, so you have to differentiate it, but if it's constant, so now xr dot is 0. So if xr is constant, the derivative is 0. So if we rearrange this equation again, you will see like the sliding surface is axr minus ax1 minus x2. And again, if we take the first derivative of the sliding surface, this will be 0 because this is constant. So it will be the derivative of x1 is x2, and x2 is the dynamic of the system. If we equal this to the reaching law and rearrange the equation, we will get the control law in this. Minus ax2, the remaining of the dynamic of the system, we take the u, and this is plus, which is a difference from the regulator when it was minus, plus k, the absolute value of the surface up to the gamma sign, the sliding surface. Now take the same example for the regulator, but instead of regulator we have reference tracking. Now the sliding surface is E plus E dot, and E is xr minus x. We will consider that we are following the unit step input, so E dot is xr minus x, and xr will be 0. So this is the final surface, A, because xr is 1, A minus ax1 minus x2. Take the first derivative, substitute it with the dynamic of the system equal to the reaching law, and rearrange the control law. You will see that u minus x2 minus the capital C, because we know the capital C but we don't know the small c, minus c2 plus k absolute of the sliding surface multiplied by the sign of the sliding surface. Now let's go to the Matlab. We see how we could implement this. So this is the call function. We will call the function. Now this is the function. So the difference is C1 and C2 we don't know for exact. We know C1 capital and C2. Now this is the A and K and PP with the tuning parameter. And you will see there's a difference between the regulator and the reference, because you have to play with these numbers until you get the desired response you want. Now this is the sliding surface as we obtain from the slide. So the sliding surface is A minus ax1 minus x2. So this is A minus ax1 x2. And this is the control law, which is minus ax2 capital C1 x2 square, so on. So this is the control law we implemented. And this is the dynamic of the system. This is x1 dot is x2 and x2 dot. And again, so important that you put C1 and C2, which is the real dynamic of the system. But in the control, we just put the upper bound value of the C1 and C2. Now, we will assume like C1, C2 is 2 and 7, it's less than 5 and 8. And we will assume that the initial condition is 0.1 and 0. And we run the system, and we will see that the x is follow the step reference, and the x dot is equal to 0 when the x is get to the 1. Now, if you change the initial conditions, so let's assume that we have minus 0.2. So you have like energy system. And again, if you just run the system is okay, there is no problem. And also, if we change the dynamic of the system, so for example, here we put 3, here we put like also 3, save, and we run the system, we still get follow the first the unit step response. We can change it, like for example, we put 0.3, this is like 2. So because we don't know how much this value are, but all we know is the maximum of this number. So we say, we run the system, and you see that whenever you change the C1, the small C1 and C2, your response is following the reference tracking without any problem. So this is all I want to explain in this. Thank you. See you next video.